Previously, we talked about measures of center of some data. Now we want to talk about measures of variation, or how much do those data vary from the center. So consider these two data sets. Data set 1 consists of the number 36, 40, and 41, and data set 2 consists of the numbers 2, 40, and 75. So these data are all fairly close together, 36, 40, and 41. These data are a little further apart, 2, 40, and 75. But it turns out if we just look at the measure of centers, so for instance, let's look at the mean and the median of each of these. The mean of this first data set is 39, and the median is 40. It turns out the mean of the second data set is 39 also, and the median is also 40. So just looking at the mean doesn't give us a good enough picture of what the data set is doing. We also want to know how far apart are all the data from that mean. The range is the first measure of variation that we'll talk about, but we don't use it that often. The range is simply the difference between the maximum and minimum data values. For example, what is the range of the following FICO credit scores? Well, to do this, we first have to identify the largest and the smallest data values, or the maximum and minimum. In this case, the maximum looks like it's 740 and the minimum looks like it's 520. So the range is simply 740 minus 520, which gives us 220. The measure of variation that we'll use more often is the standard deviation. The standard deviation of sample values is a measure of how far the data values are from the mean. The standard deviation is one number that gives us a clue as to how spread out are our data compared to the mean. So for example, if you look at these two data sets, this data in this first set is further away from what looks like the mean or the middle of our data set. Whereas in this data set, the mean, or rather the data is closer to the mean. So in the first data set, we would have a larger standard deviation, and in the second data set down below, we would have a smaller standard deviation. So in other words, the larger your standard deviation, the further spread out your data is from the center. The formula to calculate the standard deviation looks a little cryptic at first, but it's not too bad. And notice I say we use the S for the sample standard deviation. We'll compare this to the population standard deviation in a moment. So let's use this formula to calculate the standard deviation of the numbers 1, 3, and 14, and assume that 1, 3, and 14 are a sample that comes from a larger population. So we'll use our sample standard deviation formula, but notice the first thing we have to do is calculate the mean of that data in order to use the sample standard deviation. So to calculate the mean, we simply, of course, have to add 1, 3, and 4, and then divide by the total number of data, in this case, 3. So adding all that up and dividing gives us 6. Now we can go over to our standard deviation formula and plug in our numbers. So our first data point is 1, minus the mean is 6, and squared. And then we're going to add to it the next data point, 3, minus 6 squared. And then add the last data point, 14, minus 6 squared. And in the denominator, of course, n is 3, so we'll have 3 minus 1 in the denominator. So going along with PEMDAS, let's first subtract and then we'll square each of these terms. So we get 25, 9, and 64. And the denominator, we'll have 3 minus 1 gives us 2. Altogether, that comes to 7. There is a shortcut formula for the standard deviation, and at first glance this doesn't look like a shortcut. However, the one thing you may notice is that there is no x bar in this formula. In other words, we don't have to calculate the mean first to calculate the standard deviation if we use this shortcut formula. So let's try it on the same three numbers and make sure we get the same standard deviation. So in this case, n, of course, is going to represent the number of data points I have. So n will be 3 in this example. I'm going to add up all my data, but squaring them each time. And then I'm going to subtract from it what happens when I add all 3 data together and then square afterwards. So writing this out, it looks like this, where I'll have n, which is 3, times my first data squared, plus my second data squared, plus my third data squared, minus all of my data added together squared, and then divided by 3 times 3 minus 1. So again, going along with PEMDAS, I'm going to play in the first parentheses and square all those data first. In the second parentheses, I'm going to just add those together. And then, of course, I can do my 3 minus 1 in the denominator. The next thing I'll do is add these numbers together in this first parentheses. In the second parentheses, I can do the exponents. So I'll do 18 squared. And on the denominator, I'll just multiply those together. So now one more thing I have to do before putting it all together is multiply 3 times 206, and then I can subtract the numerator. So now dividing 294 by 6, you see that you get 49, and of course square root of 49 is 7, which is the same answer that we got with the other formula. So the shortcut formula is a shortcut in the sense that we didn't have to calculate the mean first. You can use either formula, whichever one comes more naturally to you. So we mentioned that there's a slightly different formula for population standard deviation. That formula looks like this, and there's a couple differences I want to talk about. The main difference is that instead of n minus 1, we have n. So n in this case is going to represent the entire population size. And we use capital N when we talk about a population. The other minor differences are the symbols that we're using. We use this Greek letter sigma, and this is a lowercase sigma, to represent the standard deviation of a population, versus S that we use for a standard deviation of a sample that comes from a larger population. We'll use mu to represent the population mean, as opposed to x bar that we use to represent a sample mean. But otherwise, the formulas are the same. The range rule of thumb for standard deviation of a sample is that the minimum usual value, or the smallest usual value that would appear in a data set, would be the mean of the data set minus 2 times the standard deviation of the data set. And the maximum usual value that would appear in your data set would be the mean plus 2 times the standard deviation. For example, suppose the mean score on an exam was 84% with a standard deviation of 6%. If Alec got a 99%, is Alec's score unusual? Well, to calculate the usual value, and namely the maximum usual value, we simply have to take the mean, which is 84%, and add 2 standard deviations to it. So the maximum usual value would be 84 plus 2 times 6. That is adding 2 standard deviations to the mean, which gives us 96%. So since Alec got a 99%, this is an unusual score. If we asked a similar question, if Alec got an 85% on the next exam, is this an unusual score? Well, you have to be careful here. I'm being a little misleading. We don't know any of the data from the next exam. In other words, we don't know what the mean was, and we don't know what the standard deviation is. So without that information, we can't talk about if this is a usual or unusual score. For all we know, everybody else maybe scored 35%, in which case this is probably an unusual exam, but we don't have any information on it. So this is really a bogus question. We can't answer it. Another measure of variation is what we call variance. A variance is almost the same thing as the standard deviation. It's simply the standard deviation but squared. So if you think about this, all that means is when we're calculating standard deviation, if we didn't take the square root of it, we'd have this measure called variance. Now we tend to talk about standard deviation more, mainly because of units and keeping the units correct for any given problem, but variance has a purpose as well. So we'll get into all that later on in the semester. But if you know the standard deviation, then the variance is just that standard deviation squared. And that'll be true for a sample or a population, standard deviation and variance. So a little bit to help us understand what the standard deviation is telling us, we have the general rule of thumb that most of the data lies within 2 standard deviations from the mean. Now that was the same idea as that general rule of thumb with the maximum usual value and the minimum usual value. But here we say it slightly differently, that most, about 95% of the data, will lie within 2 standard deviations from the mean. So for example, if we have 7 FICO scores, we calculate the mean of these scores to be 668.9 and a standard deviation of 77.1 points. Most of the data should lie within 2 standard deviations of the mean. That is, to get 514.8, I took my mean and subtracted 2 times the standard deviation. And to get 823, I took my mean and added 2 times the standard deviation. Most of my data should lie between these 2 numbers. So indeed, it's true, we have 680, 685, 690, 693, 694, and 740 that lie between these 2 numbers. We only have one that would be an unusual value, that is, in this case, unusually low. If we don't want to calculate the exact standard deviation, we can get a rough estimate of the standard deviation by simply looking at the range of this data value and dividing it by 4. So again, this is a very rough estimate of what the standard deviation is. So generally what we use this for is if we're doing the calculation for standard deviation, which as you recall is kind of a tricky formula, and you want to make sure that your answer is in the ballpark, you can do this calculation, and if your standard deviation is close to this, range divided by 4, there's a good chance you did everything correctly. If it's off from this estimation, I wouldn't necessarily say it's incorrect, but it would warrant going back and double checking your calculation. So in this case, if we computed this estimate of the standard deviation, the range is 740 minus my low score, it's 590 divided by 4, gives me about 37.5. If data has that bell shape or normal curve to it, then we have this empirical rule. About 68% of the data falls within 1 standard deviation of the mean. About 95% of the data falls within 2 standard deviations of the mean, which is the same as that general rule of thumb that we mentioned. And about 99.7% of the data falls within 3 standard deviations of the mean. IQ scores have a bell-shaped or normal distribution with a mean of 100 and a standard deviation of 15. What percentage of people have an IQ score that is between 70 and 130? Well, if you notice, Since our standard deviation is 15 and our mean is 100, 70 is 2 standard deviations below the mean. It's 30 below 100. And 130 is 2 standard deviations above the mean. So we have that 95% of IQ scores should fall between 70 and 130 based on our empirical rule. So this is just a graphical representation of the empirical rule. If this middle part represents the mean and our data is this bell-shaped or normal curve, then 68% lies within 1 standard deviation. So half of 68 is saying 34% lies above and about 34% should lie below. And then another 13.5 and 13.5 on either end would get us to 95% lies within 2 standard deviations rather, above or below the mean. And then almost all the data, 99.7, should lie above or below the mean within 3 standard deviations.